Here we're being asked to find the definite integral. So we know it's a definite integral because we've got bounds, we've got numbers above and below our integral symbol here. We're being asked to find the definite integral of this equation. 3x squared plus 10x times x cubed plus 5x squared, all of that raised to the third dx. So that information up in front, that's just saying take the antiderivative between these two values, and then the dx at the end here is telling us the variable we care about. So what we're looking to take the antiderivative of is this stuff in the middle. If you look down on your page and you see that you've got more than a bunch of stuff being added and subtracted, you know you're not just going to apply the power rule for this. And so here, if we look at this right now, we've got things being multiplied, we've got stuff inside of parentheses raised to powers, so we definitely got a lot more than just a bunch of stuff being added and subtracted. It's also not fitting any of your special case antiderivatives, so those ones that you just have to have memorized, those trig functions, natural logs, all of those. It's not that either. And so the nice thing about antiderivatives are if it's not in those two categories, you pretty much know what your only other method is, which is going to be to do what's called U-Substitution. So U-Substitution is a set of side work. So it's the same set of side work every single time you do it. Once you get your steps down, you're just going to need to go through that process anytime you run into a U-Substitution, and you'll get through them no problem, I tell you. It seems crazy at first, but you'll be rocking through these U-Subs before you know it. Step one of the U-Substitution process is going to be to choose our U value. I've developed my own little priority list over time. There's nothing hard and fast about it, but it definitely helps me when I'm looking, so I give it to you as well. The first thing I go looking for if it's available is a natural log. If I see that, that's what I want to select for my U. If that's not available, I look for what I refer to as the inside piece, as if you were doing a chain rule problem. So if you've got something inside a power. The third thing that I would go looking for is the bottom of a fraction, if that other stuff isn't available. So whatever that full bottom of the fraction is. And then kind of the last thing I'm generally looking for is I want to usually try to find the piece that has the highest power of x. So working through my options right now, I start at the top and I say, okay, do I have a natural log? Well, there is no natural log over in this equation, so I'm not going to choose that. I then move down to the next option, which is inside piece. I definitely do have that. This x to the third plus 5x squared, that got plugged inside that third power there. This is also the chunk that has the highest power of x, so it's doing a couple of things that I like. So I start off and I choose my u. So the u in this situation is going to be x cubed plus 5x squared. From there, the next set of steps is always the same. So we come through, and the next part of this is you're going to need to take the derivative of that u. So we get du dx. You always want to use that differential notation when you're doing this work. Du dx equals, and then we're taking the derivative of the stuff on the right-hand side. So we're doing our power rule for derivatives. So that says bring the power down and then subtract 1 from the power. Then plus, again, bring the power down. 2 times 5 gets us 10. X, subtract 1 from the power. The next part of our process here is when we go to substitute back into this original equation, we need that equation to be talking nothing but the language of u. So right now it has a dx in it, and we need to change that dx over to a du. And this is where my method I really like it more than probably the way you get taught in class. And it's just one little step further, and it changes how simple these problems can be dramatically. It'll blow your mind. So we need to solve this equation to get dx by itself. So the first thing you're going to do is you're going to multiply both sides by dx. We're treating dx like any other variable, and we're just trying to get it alone on one side of our equals. So then those dx's cancel out. We're left with du equals 3x squared plus 10x dx. And then I go ahead and getting dx by itself, I can now divide both sides by 3x squared plus 10x. Divide by 3x squared plus 10x, and out of there we get du over 3x squared plus 10x is going to equal dx. This is going to save you, a lot of times in this section they talk about you needing to see something. This is going to save you from ever having to see anything when we do this process. On definite integral problems only, we get one additional step here. So on an indefinite integral problem, you just do those first 3 steps. On a definite integral problem, remember that we have bounds up here. These are x values. We only want to be talking the language of u, and so we now need to adjust the bounds to talk that language of u. To do that, what you're going to use is you're going to use your equation up here that relates u and x to each other. So we know that when x equals 7, we're going to plug that into this u equation here. And so we'll get out of there that u equals, instead of x, we plug in 7 to the third plus 5, and then instead of x, plug in 7 and then squared. And so then what that gets us out of there is our new upper bound. So that'll be 588. Pop that into a calculator, whatever you need to do. Then we play the same game with our lower bound. So x was 3. We plug that into our u equation. So we get 3 to the third plus 5, and everywhere we see an x, plug in that 3 squared. And our new lower bound is now going to be 72. So here at this point, we are ready to actually go and do the substitution part of this problem. So what you're going to do is you're going to go back to your original problem and you're going to work your way left to right through it. And it's either one of the things that you're substituting in for, our u, our dx, or our bounds, or you leave it alone for the time being. So coming through, we first need to readjust our bounds. So our new upper bound is 588. Our new lower bound is 72. We just calculated those out. Nothing happened to that 3x squared up front yet. So that is all still there. Then this stuff inside there, that became our u to the third. And then dx becomes our du over 3x squared plus 10x. So at this point in the process, any u's or any x's that were left in the problem should hopefully cancel out with x's you plugged into the problem. We need to get this thing down to talking the language of u. If that doesn't happen, stop. You might have chose the wrong u. You might have messed up some of your algebra, but just take a second look. Here, we get exactly what we expect. 3x squared plus 10x cancels with 3x squared plus 10x. Now what you're going to do is you're going to rewrite this problem. So we're now looking at the definite integral from 72 to 588 of u to the third and then du. This right here, this is what I call your reward for all of that hard work. A brand new math problem. So ideally what we've done now is taken something we couldn't do the antiderivative of and turned it into something we can take the antiderivative of. So to take the antiderivative of this, we just need to follow our power rule now for antiderivatives. So we just want to do our add 1 to the power, and then step 2 of that, divide by the new power. So then working our way through this, we add 1 to the power, that gets us u to the fourth, divide by that new power, and because this is a definite integral, we have bounds. So we say evaluated from u equals 72, because these are u values, to u equals 588. And now to finish this off, you apply what I just call the top minus bottom process. You're going to take the top value, plug it into this equation, and then subtract off of that the bottom value plugged in. So we're going to get 588 to the fourth over 4. That is our top value plugged in minus our bottom value plugged in. So 72 to the fourth over 4. And then, of course, you're just going to end up shoving that into a calculator. And out of there, you are going to get this monster of all monsters. You're going to get this huge number. What is it, like 29,878,000? 9,920. That right there is the net area between the curve and the x-axis of the equation we started off with. So U-substitution allowed us to take an antiderivative that we couldn't handle, reward ourselves with an antiderivative that we could handle, and that allowed us to get to our final answer for our definite integral. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.